Hello and welcome to what will probably be a relatively chunky overview of mixed effects models and how to use them in R. And this is going to be a conceptual introduction rather than a formula written overview of mixed effects models. So if you want to understand the concept behind them and how they work in practice rather than the underlying math, then this would be a good video for you. So to start off with, there are many names for the same thing. So mixed effects models are also called nested models, random effects models, random coefficient models, multi-level models, and the name that they're called by is often dependent on the discipline that is calling them a name. So in psychology, we often call mixed effects, or we often call such models mixed effects models. So I'm going to continue using that terminology throughout this presentation because I come from psychology. So I'm going to call them mixed effects models. But regardless of what the name is, they all refer to a type of data that has multiple levels, multiple clusters, multiple effects, and nested groups. So I'm going to kind of go over that in a little bit of detail now. So it's called a mixed effects model because it has a fixed effects, which is what we normally include in a general linear regression, and random effects, which is the part that takes into account the different levels of the different levels of the clusters and so on. And that's why it's called a mixed effects model, because it incorporates both fixed effects and random effects. So fixed effects are variables that we expect to have an effect on the dependent variable, on the y variable. And these will be called predictors in a standard linear regression. And in an experimental setting, fixed effects are often the primary variable of interest to the researcher and represent the overall or population level average effect of the specific model, i.e. a main effect or an interaction between two main effects. On the other hand, random effects are usually grouping factors for which we are trying to control. So we're trying to account for the variance that these grouping factors have on our model, on our fixed effects. So random effects capture the random variability in data that comes from different sources. Often this will be participants, but it can also be different items that you use as stimuli. So by specifying random effects of our sample, we're able to factor out some of the idiosyncrasies of our sample and obtain a more general estimate of the fixed effects of interest. So by removing some sample-specific variance, it allows us to have a much broader interpretation and application of the model. The random effects are almost always categorical variables. In fact, I've never had an instance where it was not a categorical variable. But I'm sure it exists in some sense, in some abstract manner. So a model which contains both these fixed effects and random effects is a mixed effect model. So the terminology of mixed effects model is quite clear. You have your predictors as fixed effects, and you have your random effects as sample specific idiosyncrasies that you want to kind of cancel out or account for. Okay. So I said that mixed effects models are data dependent. So some examples of data that has mixed effects would be that students, which is the fixed effects, are nested within schools, which would be a random effect. Children, fixed, are nested within families, random. Employees, fixed, are nested within their organization, random. Repeated measures, which would be fixed, are nested within participants, which have random idiosyncrasies. We want to kind of cancel out the sample-specific random effects of schools, families, organization, and participants. So we want to kind of cancel out these random effects, or at least account for them in our model. So how many levels does a random effect need to have to be treated as a random effect? So if you have organization as level, how many organizations do you need to treat it as a random effect? Some authors, such as Gelman and Hill, say around 5 to 6 levels. Anything else should be treated as a fixed effect. So treating gender and sex as a random effect would probably not be a good estimate of between cluster variance. So what are mixed effects models? Mixed effects models are statistical models for analyzing the relationships between variables measured at different levels of the data structure. So mixed effects models can be viewed as extensions to single-level models, such as the linear regression or logistic regression models. And as we've kind of gone over in the previous slides, mixed effects models allow us to account for some variability that exists in our data structure that is non-systematic, i.e. idiosyncratic or random. In psychology, commonly the participant is treated as a non-systematic random variable, and this is only the case when there are multiple trials per participant. So if you just have one row of data per participant, that obviously won't work because there's no nesting, it's just a single point of data. Okay, so you might be thinking, instead of accounting for multiple instances of the same participant or the same organization as a cluster or random effect, why can't I just average the data based on the groups and use a simple linear model? So for instance, each participant completes 10 trials of a word recall task. This would be longitudinal data, right? So multiple instances for each participant of a word recall task. Option A, we can aggregate the number of items recalled on these 10 trials so that we end up with an average score per participant. So one row of data per participant with an average score based on the 10 trials. Option B, we can model the effect of by-participant variation in the model. So we can account for variation that occurs between or within the participants themselves. So here we have more data points, right? So you have 10 data points for each participant as opposed to just one. And the model knows that there are multiple responses per subject. In that case, we have resolved issues of non-independencies. So of course the assumption of independence needs to be applied to mixed effects models as it would do in a normal linear model. So let's work with some example data and work our way through mixed effects models based on that. So using some data by Winter and Grawunder in 2012, which investigates the relationship between pitch and politeness between males and females, we can see over here that we have a subject F1, so there's multiple rows of data for each subject. This is just one subject called female 1, gender, female, scenario 1, 2, and 3. So even scenario is clustered because there's multiple levels per scenario. We have attitude, so polite and informal, and then overall pitch frequency. So the data is longitudinal because it has multiple rows per participant and has multiple blocks or scenarios. The dependent variable is the pitch frequency, and the independent variables are attitude, polite versus informal, and gender, male and female. Okay, pretty straightforward. Okay, so let's say we wanted to just do a simple regression first, right? And we aggregate the pitch scores by subject. But we leave the attitude category so that there's essentially 2 rows of data per participant, one belonging to the informal category and one belonging to the polite category. And then we have the gender of the participant as well. So F1, F2, F3 are females, M3, M4, M7 are males, right? This is just a subset of the data, not the full data set. So we aggregate our frequency for each participant based on their attitude group. So female 1, average frequency for all of their trials that were informal, and female 1 for all trials that were polite, and then aggregate those into an average frequency for that participant for that attitude. Okay, so normally we wouldn't be able to do this because it is repeated measures data. So because the same participant is listed twice, they are not independent, or they're not independent observations, but I'm just doing this as an example. This data now disregards by subject variation. So let's look at what an outcome would be in this situation. So let's do a simple regression. So essentially we just have we create our model 1 and assigned the function of linear model, our dependent variable of frequency here, predicted by attitude and gender, using our data set of I've called it politeness aggregated. And then a summary of our model 1. This shows our coefficients. Here we can see it's pretty simple interpretation. There's no meaningful differences between informal and formal attitudes. So looking at the polite versus informal when controlling for gender, which is itself a significant variable. So obviously males would have a lower average pitch frequency than females, because that's just anatomically that makes sense. Okay, so that would be a simple regression, and it obviously doesn't take into account the complete data structure, so it's not great, right? Okay, so what if we wanted to investigate a situation where we just wanted to find out how much variation that exists between the subjects, right? So based on our previous wording, to what extent does within participant variation affect the overall variance of the model, right? How much noise is there within participants? So this will be called a variance component model. So this includes just the random effects and no fixed effects, right? So here would be our code. So we have this one called model 2 assigned to the function of LMER. So this is linear mixed effects regression. It's the LME4 package. We are predicting frequency by the intercept represented by 1. And we're looking at the random effects. So be parentheses 1 line, probably a more specific word for that, but line subject, because that is our, if we go back to our data, that is our participant, or it's the name of the variable for our participant column. Okay. So now we are kind of looking at the variance that exists within each participant themselves and how much that can explain using our data of politeness, right? So this allows us to see how much bi-subject variability impacts the dependent variable of frequency. So we can also calculate so if we run this model, on this side we can see the output, right? So because we're only looking at random effects, we'll look at this random effects little block here, right? So we can see our group is subject, and our total subject variance is 3,961. Now this residual here stands for the variability that is not due to the subject. So there's some variability that exists in the data that can't be attributed to the subject themselves. So if we wanted to get the percentage of variance that is accounted for by subject specifically, then we would combine the two levels of variance and then divide the overall subject variance by this total number. So 3961 point a little bit divided by the sum of 3961 plus 941, so the residual as well. And that gives us approximately 81%, which would be the subject. So this can be interpreted as 81% of the variance of frequency can be accounted for by the subjects within the model. That means 19% is unknown, right? So 81% seems like a lot, and it is a lot, but it's also the only thing that the model is assessing. So once we add more fixed effects, then that percentage of variance accounted for by the subject should go down if it has any type of predictive capability. Okay, and that would be a variance component only model, and there might be some situations where that would be important to have. So what if we add in another random effect, right? So we're still only on variance component models, but now we have two variances to incorporate into our model. So both the item and the subject are considered random effects in this data. So let's model them as such. So you see how the equation has been, or see how the code has changed. We're still predicting frequency. We're still including the random or the intercept, and then we're including the random effects of subjects plus the random effects of scenario, and then modeling by the politeness dataset. So these have their own random effects parentheses because they're not nested random effects. So for instance, if we had schools within neighborhoods, that would be nested within the same set of parentheses, so the model knows that these are nested random effects and not separate random effects. So we run this model, right, and here's the output. So we have random effects, and instead of having just the subject, we now have scenario and subject, right? And then of course we have our residual, which has gone down a bit, because now we have a new variable that accounts for some of that residual that we didn't know what was before. So subject's still around the same, but our residual has gone down. So again, variance for the subject has gone down a bit, but not by much. Unaccounted for error has decreased substantially because we added a new variable. So the different scenarios, which we can see that there were 7 different levels of scenarios, accounted for only 4% of the variability in the frequency variable, our dependent variable, which is substantially less than the variability counted within the subjects. So the scenarios were just different contexts in which the stimuli were presented. The context in which the stimuli were presented was far less important for the variability than the participants themselves. Okay. Right, so if we wanted to plot the random effects, we can using this a neat little bit of code. So dot plot is the package, or the command. Random effects tells us that we want the random effects of model 3, and the conditional variance should be true. Right, so if we look at these models, or these plots, 0 represents the overall average of all participants and all conditions combined, right? So if we wanted to have a look at the influence of scenario, the random effects, you can see that the first scenario had quite resulted in a lower frequency than average, whereas the fourth scenario resulted in a higher frequency than average. Not sure what those scenarios are exactly, but of course if you own the data and you run an experiment, then you would have a much better idea. In terms of subjects, we can see that male 7, compared to the average voices of all participants, had a substantially lower pitch level than average, and female 2 had a substantially higher pitch than average. In fact, all of the males presented here had a lower pitch than average, and all females had a higher pitch than average. We can tell that that is the subject variance that needs to be accounted for in determining the frequency, right? So we can tell there's a lot of variance, particularly in subjects, not so much in scenario, but they should both be accounted for. And that's just how, if you want to kind of have a visualization on what your different random effects and how they affect the data, that would be a good way to do it. Okay, so we want to move on to a full mixed effects model, right? And in this case, I haven't spoken about packages, but to run linear mixed effects models, you would use LME4 package, and it's also helpful to install the LMER test package, and this gives p-values when the summary command is used. Alright, so kind of useful, otherwise you just have to interpret the critical value, which if you know how to do it, it's fine. But if you want a little bit of ease, install that LMER test package as well. Right, so here we have model 4. So this is our fourth model, right? So we're getting somewhere. Here in our model 4, we're using LMER, looking at predicting frequency by, now we have our fixed effects, so attitude and gender, plus our random effects of subject, plus our random effect of scenario by the dataset called politeness. Okay? So we're modeling the effect of attitudes in formal versus polite and sex, male versus female, while accounting for the variation in subjects and different scenarios. Yeah. So it's getting pretty complicated, right? But this is a good model in terms of treating the data as it is organically, as opposed to doing some type of transformations which are not appropriate to the structure, right? So just looking at our fixed effects only, we can see that now our attitude variable has changed. So based on whether a participant is being polite or informal, there is a substantial difference, in this case, a reduction in frequency pitch. So when they are being polite, frequency of the pitch is lower than when they are being informal. Okay? And that is statistically significant. Gender, male would have compared to female, would have a substantially lower pitch than female. So that is that's strong enough that it wouldn't change, regardless of whether you aggregate the data or not. But really, it's the attitude that is the primary variable of interest rather than the gender or the sex of the participants. So if we wanted to look at our estimates, so our estimate of attitude would be 19 and our gender would be 108. That is pretty much unchanged, right? Our average estimate is 19, and now for our attitude variable, -19, and our gender variable is just below it at 107.95. So our estimates are largely the same. But now have a look at our standard errors, right? 14.43 for attitude, 14.43 for gender. So if we wanted to have a look there, oopsie, wrong one. Our standard errors for attitude have decreased substantially, right? And that in turn has allowed us to have a significant outcome, as opposed to a larger standard error, which was rather inflated due to our aggregation. So our standard error and our subsequent t-values have changed due to how we treat the data. Both attitude and gender are now meaningful predictors. Now, that isn't to say that every data that you treat as a mixed effects model will result in a significant outcome. That's not true. But we're treating the data as it should be treated, not artificially aggregating it so that one row per one participant is modeled. Okay. So now let's look at our random effects, right? So we can see that our variance right away, we can see that it is reduced substantially, particularly for the subject. So we can see that our overall variance in the data has been reduced due to the inclusion of fixed effects, primarily gender in this case, as there is a systematic relationship between pitch and gender. But subject still accounts for 42% of the variance. Scenario now accounts for 15%, so it's an increase from 4%, and the rest is due to factors that we have not taken into account. So, for instance, the environment in which the experiment was held. Okay, so we still have some residual variance that we can't account for. Or our data, we haven't collected data which accounts for that variance. So if we wanted to add them all up again, or get the total variance component, we would sum all of the variances and then divide the specific one that we're looking at by the total, right? Let's just say we wanted to have a model which treated gender as a control variable, right? So we're not actually interested in whether males and females have different levels of variation, but in pitch, but we just want to kind of control for that effect. Okay, and then we want to test the effect of the variable of interest, which is politeness, against this control model. I called it a null model here, but it should really be a control model. Let me change that. There we go. So if we wanted to do this, we can conduct what's called a likelihood ratio test. And in this case, we need to make some adjustments to the model code. So we need to set REML, which is restricted maximum likelihood, to false. So restricted maximum likelihood, it controls something called the shrinkage of the standard error. So the standard error without REML would likely increase a little bit, but it won't have too much of an effect. Our outcomes won't change in terms of our overall interpretation, but we have to set it to false if we want to use these likelihood ratio tests. Okay, so we have our one model, model 5, which just has gender and our random effects, and model 6, which has attitude plus gender and our random effects. So now we would run this command called ANOVA. It's not like analysis of variance as you would expect it. It does a likelihood ratio test on the log likelihood of the model itself. So it's a determination of the model fit, essentially. Yeah, so this would be an outcome of our ANOVA summary. ANOVA model 5 compared to model 6. So model 6 is our one where we're testing the variable of interest. And we can see that model 6 has a lower or a better fit than model 5. Looking at the AIC, the BIC, and essentially the statistic that's been tested here is the log likelihood. That's why it's called a log likelihood test. And we can see that negative 403 compared to negative 397, closer to 0, is better. Our model 6 is numerically better, but conducting a chi-square test, it's also statistically better. Now you could interpret this and report the summary as being that the influence of attitude is statistically significant on the outcome, right? That is essentially how you model, interpret, and compare mixed effects models. But we've only been working with random effects, which is called a random intercept model, right? So the intercept is their positioning on the y-axis, the starting point on the y-axis. And I'll show some illustrations to kind of get that point across. But I think about it as their starting point on the y-axis, but the slope itself, regardless of the participant or the subject or the scenario, in this case of the random effect, is fixed. Okay, they always point in the same direction, at the same angle, at the same slope, at the same steepness. That's what you get with a random intercept model with fixed slopes. But we can include a random slope so that the angle or the degree of each of those lines, per se, can differ by participant or by scenario, by mixed effect. As an illustration of this, right? So by including random effects, we allow for each participant and each scenario to have a different intercept. It's again the baseline starting point for the pitch frequency. But the slope, not the slop, of the relationship is fixed. We assume that the effect of politeness will be the same for all subjects and all scenarios. But that's probably an incorrect assumption, right? But we can test that assumption. So here we go. If we look at the coefficients for model 6 and our random effects of scenario, the effect of politeness is exactly the same for each of them. Likewise, the effect of gender is the same for each of the different scenarios. Likewise, subject, the effect of attitude is the same, and gender is the same on all of our different intercepts. So the intercept would be the starting point on the y-axis, and the slope would be determined by the intercept here. But we can change that so that each of the levels of the mixed effects can have a random slope as well. So we can change that, like I said. We can change our model so that it includes random slopes. So here's model 7, right? So we have a linear mixed effects model. We're predicting frequency with the fixed effects of attitude and gender. And now here comes the change, right? So we want a random slope based on attitude. We want our attitude to affect our random effects. Okay, so here we would, normally we just had the intercept only, but now we have an intercept plus attitude, getting the random intercepts of subjects plus, or the random effects of subjects, plus we have the random slopes of attitude by the random effects of scenario. Looking at our data, politeness, and REML. Actually, in this case, it could be REML equals true, or REML as default is true, because we're not doing any model comparisons. But for the sake of this, let's just leave it like that. So now we have a different effect of slope for each subject and each item. They all have the same sign and are relatively similar. So this is the output. So they're all negative, and they're all between -15 and -23 as an intercept. So not that far away from each other on the y-axis. And this indicates that despite individual variation, there is a consistency in the effect of politeness on the pitch of voice, i.e., it reduces the pitch. Okay? Now, gender is the same because we didn't add random slopes for gender, but if we could, if we wanted to. In fact, some people recommend that we should always go for a maximal effects model. So we account for the random slopes and random intercepts of each of the fixed effects that we're looking at. But that's up to you. So, should you add random slopes? Here's a question, right? It makes sense that people would differ in the degree, i.e. the slope of their reaction to an experimental manipulation. Barr suggested, again, that's what I said earlier, Barr suggested we should keep it maximal, at least for controlled experiments. So include all of these random slopes based on your experimental manipulations. And we should include random effects for all fixed effects of primary interest, such as politeness, but not gender, as it was a control variable. So we only want to control for the variance that gender would have on the attitude, not gender as a fixed effect, because it's not really of interest, right? So should you add random slopes? That is up to you and the context in which you derived your data. So an illustration of random intercepts, right? So if we had random intercepts only, for instance, if we go back to this point, so we can see that all of our intercepts are exactly the same, right? I mean, we can see all of our slopes are exactly the same, but our intercepts differ slightly. So here we go. Our slopes are all pointing in the exact same direction at the same level. Only our intercepts at a different starting position have changed. If we have random slopes only, but no intercepts, then all of our intercepts would start on the same point, but our slopes would differ in the degree of their strength. Now, if we had random intercepts and random slopes, they would start in a different point, start in a different intercept, and the actual direction of the slope, or the severity or the strength of the slope, would differ as well. So that is the ultimate mixed effects model. But whether you should use random effects as well as random slopes depends on whether it would be appropriate for the data. So only you could know that, right? And that is the conclusion of this little seminar, this workshop on mixed effects models. And if you're interested, here are some additional references. go forth and apply if you want to. And thanks for watching, and if you hope you found it useful. If you do, drop a like, subscribe, and so on.